Hi, I'm Jungwoo from KAIST in Korea. In this video, we present joint demosaicing and deghosting of time-varying exposures for SingleShot HDR imaging. SingleShot HDR imaging is a task that performs HDR imaging based on image sensor values obtained with a single shot. Typically, to achieve this, a spatially varying exposure sensor is used, where neighboring pixels have different exposure levels. SingleShot HDR imaging allows us to extend the dynamic range of the captured scene since it obtains information from multiple exposure levels in a single shot. However, one drawback is that the RGB color value is reduced to acquire multi-exposure level information. In a camera, ISO gain and exposure time determine exposure levels. Adjusting exposure levels with gain may result in a limited extension of dynamic range compared to exposure time-based methods, and excessive gain amplification can introduce a significant amount of noise. On the other hand, exposure time-based methods effectively expand dynamic range because they control the amount of incoming light. However, this can lead to different levels of motion blur, which is often referred to as ghost artifacts. Our goal is to reconstruct an HDR image from the given time-varying Caught-Bayer pattern sensor input. We propose an HDR reconstruction network that jointly solves both the demosaicing and deghosting problems. Since there is no public dataset that matches our goal, we create a synthetic dataset using a public HDR video dataset. To generate this synthetic dataset, we follow three main steps. First, as the HDR video dataset consists of a sequence of HDR images, we add consecutive images for each exposure time to compute the radiance values. Second, we use these radiance values to generate raw images for each exposure level and add simulated noise. Finally, we sample these images according to the input Bayer pattern. The corresponding ground truth for the create input Bayer image is an HDR image of the very first frame. We also create a real-world test dataset by directly capturing scenes using a DSLR camera. The process is similar to creating the synthetic dataset with a few differences. First, instead of using an HDR image sequence, we utilized a DSLR burst shot sequence. And we don't add additional simulated noise as it already contains the innate noise in the real-world photography process. In order to jointly solve both the demosaicing and deghosting problems, we propose a network that takes a Caught-Bayer raw image as input and reconstructs HDR images at the same resolution. Our network can be divided into three main components. First, preprocessing step performs exposure normalization and both channel-wise and exposure-wise subsampling. Next, CNN-based feature extraction is for spatial resolution enhancement and demosaicing. Lastly, feature registration module registers different motion blur between exposure levels. For feature registration, we adopt multiscale transformer architecture from various feature extractions. For each transformer block, we use exposure alignment operation instead of the self-attention at general transformer block. Our exposure alignment module performs cross-attention with other exposure feature. For instance, to get the exposure alignment result of exposure level 1, we concatenate the cross-attention result from the feature of exposure level 2 and level 3. By employing this explicit permutation, each feature vector of the exposure level effectively addresses spatial misalignment and motion blur. This is the result of the synthetic dataset. Our proposed method shows promising results both qualitative and quantitative comparison. This is the result of real-world dataset. Our network effectively registers different motion blur. In this work, we propose a novel single-shot HDR imaging technique that tackles the demosaicing and deghosting problem of time-varying exposures. To accomplish this, we create a dataset of time-varying cut-Bayer pattern HDR sensor inputs from existing HDR video datasets. We address spatial misalignment and motion blur in longer exposure channels through the transformer architecture by acquiring query, key, and value vectors from various sources in the transformer block. Thank you for the listening.